Assalamualaikum and a very good afternoon. Okay, so today we are going to discuss another two remaining Fourier transform properties, which are the differentiation, integration, and also duality. Okay, let's start with the first properties for this session. So differentiation, as usual, if you have Vt, so the equation in frequency domain is V omega. And if you have a derivative equation with the order number of n, so the Fourier transform of Rt is R omega equal to J omega to the power of order number V omega. So V omega is from the basic equation. So given an example, Vt equal to rectangular t and Rt is given as the second order derivative equation. So refer to the table for Vt. So Vt is rectangular t. So Vt is rectangular t. T over tau meaning 1. So in this case your tau equal to 1. So your V omega equal to A tau. So your A equal to 1. 1 and the tau also 1. Sinc function omega tau equal to 1 omega over 2. Okay, next you need to find what is R omega. So R omega is the second derivative of Vt. So in this case, R omega equal to J omega to the power of the order number. So the order number is 2, V omega. So what is your V omega just now? It is sin omega over 2. So replace your V omega into R omega equation and then simplify your final equation. So in this case, J squared equal to minus 1. So that's why you get negative here. Okay, second example. Find the Fourier transform of Vt if given the first order differentiation and second order differentiation as the figure shown. Okay, so to start with, you need to identify what is the equation of the first order differentiation and the second order differentiation. So for the first order differentiation, so how you get this from Vt? So you need to know what is the equation of Vt. So in this case, you can see that Vt equal to so basic equation y equal to mx plus c. So in this case, Vt equal to the slope or the gradient is a over 1. So is a t plus a. Okay, so when you differentiate this, you'll get constant a. So that's why from negative 1 to 0, you have constant a. Okay, and then same goes to the second side. So it is negative slope, so a over 1 divided by minus 1. That's why you get negative 1 as the constant from 0 to 1. Okay, so this is the first derivative equation or signal from Vt. So for second order differentiation, so you have from here, just look at the vertical line. So you have one positive and this one negative and this one positive. So at negative 1 it is positive a, and then at 0 it is a to negative a is negative 2a because it's pointing down, and at 1 it is positive 1. Okay, so let's write the equation. So the first one, this one, So dvt over dt is equal to a rectangular t plus 0.5. So this is negative a, so it's supposed to be negative. So negative a rectangular t minus 0.5. So how you get this equation? Go back to basic rectangular signal. So this is rectangular signal. So negative 0.5, sorry, positive 0.5 and negative 0.5, the amplitude is A. So this is a rectangular T over tau, in which it is equal to 1 rectangular T, in which the tau is the width of the rectangular, so the width is 1. Okay, so but now the signal has been shifted to the left by, so to get into this shape, so to get into this shape 0 to negative 1, you see that the signal being shifted to the left by 0.5. Okay, so when this one shifted to the left by 0.5, it becomes negative 1. So 0.5 shifted to the left by 0.5, you get 0. The amplitude is still 1. So that's, or in this case, the amplitude is A. So that's why you get A rectangular, T, the signal being shifted to the left, A rectangular, T minus to the left negative 0.5. That's why you get AT plus 0.5 minus the right hand side, A rectangular T, the signal being shifted to the right by 0.5. So that's why T negative positive 0.5. So the signal being shifted to the right by 0.5. Okay, so second equation for the second order differentiation. So given by the impulse function, so the magnitude is A del t minus 1. So this is on the left hand side, and this is the middle one at t equal to 0, and this is at t equal to 1. Okay, so let's solve. So the first order differentiation, so this is the first order differentiation. So the Fourier transform for this differentiation equal to j omega to the power of n. So in this case, it's the power of 1, n is 1, so the power of 1 v omega. So the right hand side also perform the Fourier transform for the right hand side as well. So the first order differentiation equal to a rectangular t plus 0.5 minus a rectangular t minus 0.5. So perform the Fourier transform on the right hand side as well. So this one equal to a sin omega over 2. So since there's shifting, so refer to the table when you have time shift, so the signal will be having multiplication by exponential function. Okay, same goes to the second component, a rectangular become a sinc function. Also there's time shift, so multiplication with exponential function. So now solve for v omega. So v omega equal to, so this j omega being moved to the right hand side. So now the equation can be simplified to this. So if you notice, this is basically the shape of sin function. Okay, so sin function in exponential e j omega t minus e minus j omega t divided by 2j. So modify the equation a bit. At the end, you will get v omega equal to a sin squared omega over 2. Okay, same goes to the second order differentiation. So you need to perform the Fourier transform both sides. So this is when you have differentiation on the left hand side, you need to perform the Fourier transform on the right hand side as well. So please refer to the table 2 for the Fourier transform of this specific function. Okay, so in this case, for the differentiation, so the Fourier transform is j omega to the power of n, so n equal to 2 p omega. So the equation of the impulse function equal to this. So from the table, if you have impulse function with shifting, so you'll be have in Fourier transform, it will be ae minus j omega t naught. So from here you can identify the t naught. So in this case, t minus t naught. So your t naught is negative 1. And in here, t minus positive 1. So this is your t naught for the second function. So in this case, your t naught is positive 1, and the other one, the t naught is negative 1. Okay, so then solve for v omega. So v omega equal to 4a omega squared sine squared omega over 2. So in this case, some modification is made. Okay, if you have the Fourier the identity, the trigonometric identity, so you can use that to simplify the equation. Okay, next Fourier transform properties is integration. So same thing, refer to the table for the Fourier transform equation. If you have an integration of v t dt or v tau d tau in this case, so the Fourier transform of RT is R omega given by this equation. Okay, let's look at the example. Given Vt equal to rectangular t, so obviously you need to find what is your V omega. Okay, so obviously when you have rectangular function, so the output will be in sinc function. So basic equation, a rectangular t over tau will be producing a tau sinc function omega tau over 2. Okay, so in this case, you have the Vt given by rectangular t, t meaning that the tau is 1 and a also 1, so you get the Fourier transform is a is 1, tau is 1, sinc function, tau is 1, so omega over 2. Okay, so what is R omega then? So RT given by this differentiation equation, so R omega equal to this equation basically, but providing that this condition V naught will be 0 when omega equal to 0. So in this case, just replace the equation with V naught equal to 0. So therefore, this one is 0. So your R omega equal to 1 over j omega multiplied with V omega. So what is your V omega? It is from the rectangular function. So your the output of integration for RT is R omega equal to this equation. Okay, the last properties of Fourier transform is duality. Duality is happening when you cannot find the function in time domain, but you can find the function in frequency domain. Okay, so usually you will see that the small letter Vt produce V omega. So this is the Fourier transform or the frequency domain equation. So, but in some cases, you may notice that there's capital Vt. So what is the Fourier transform of this function? So let's look at the example. So given gt equal to a tau sinc function t tau over 2. So obviously you know that when you have a function of Vt, a rectangular t over tau, so this one will produce V omega, the capital V omega. It is a tau sinc function omega tau over 2. But in this case, the sinc function is in t. It is not in omega. Okay, so you need to switch the location. Okay, this is from general equation. So now this equation being moved to the left hand side. So a tau sinc function, but omega, okay, in this side is all t equation, on the other side, on the right hand side is all omega equation. But now you see sinc function using t. So when you move this sinc function to the left hand side, so the omega will be replaced by t. Okay, and then the rest is the same. Okay, and then on the right hand side, so what is the Fourier transform? So the Fourier transform of this, so you need to switch this one into this location. So multiply with 2 pi. So just copy the equation a rectangular. So remember this side is for omega. So it is omega over tau, but given negative sign. Okay. Okay, this is the representation of signals having duality properties. So this is general or fundamental signal. If you have rectangular, so in frequency domain you have sinc function, but in this case you have capital G, but in t domain you have the sinc function, but in time domain. So the Fourier transform of this function, you need to solve it using duality. So it will produce g omega. It is in rectangular function, but don't forget to multiply with 2 pi, and then the function a rectangular, and the t will become negative omega over tau. Okay, let's look at one example on duality. So an LTI system used in valve control is shown in figure Q2b. The system is said to be injected with the input of xt. Okay, this is the input signal. Xt equal to 5 over pi sinc 5t. It was noted that the feedback signal h1 omega equal to this equation. So obtain the Fourier transform of the input signal. So this is the input signal. So if you notice that it is in t domain, but there's sinc, so obviously sinc usually for frequency domain, so meaning that you need to apply duality concept here. And let's look at the given example. So the input signal given is xt, y capital X, because you notice it is sinc. So sinc function usually used in frequency domain. Okay, but now you have the sinc function in t domain. So obviously to solve this, when you cannot find the sinc function in t in time domain, so you need to use duality concept. So the basic equation, if you have xt, it is a rectangular t over tau. So your x omega equal to a tau sinc function omega tau over 2. Okay, but in duality concept, you have this equation in t. So it becomes a tau sinc function t tau over 2. And this, the Fourier transform of this equal to 2 pi a rectangular, replace t with negative omega over tau. So now compare the given equation with yours. So your xt equal to 5 over pi sinc function 5t. So it will produce something like this, but you need to identify what is your a and the tau. So from here, a tau equal to 5 over pi and tau over 2 equal to 5. So tau so in this case, so tau over 2 equal to 5. So therefore your tau equal to 10. And then a tau equal to 5 over pi. Therefore a10 equal to 5 over pi. So you can find a equal to 1 over 2 pi. So therefore your answer will be 2 pi. Your a is 1 over 2 pi rectangular negative omega over 10. So simplify the equation. So the Fourier transform of this function x omega equal to rectangular negative omega over 10. Okay, so for second question, find the Fourier transform of the output. So I'll leave it to you. So we will discuss this in next session. Thank you.